La 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 la. Did you hear that? If so, then let me know in the chat. I think the audio is back now. And let's start again. So, hey everybody, and welcome back to episode number 4 already of the Raspberry Pi Emulator live coding hacking. And while I'm waiting for your comment in the chat to see if the audio issue is gone and you can hear me now correctly, loud and clear, perfect, thank you. Let me share my screen again and remind us what we did last time. So last time we were getting this UART, hello UART program to work in the simulator, and we had this joyous moment where we actually got the output from the program in our simulator. And then we spent a few minutes reflecting where to go next, and we decided to start working on the boot process, on loading and simulating the Bootrom. So there we went to this document and basically tried to figure out the sequence for the Bootrom. And I think we also started looking at the code because I have it open here. Yeah, it was a great temptation to go ahead and keep hacking on the project during the week, but I know you asked not to do this, so I kept everything here for now. So first of all, I think let's close all these all their tabs. We don't need them anymore. And then let's go and see what's up with the Bootrom. So yeah, so this is the disassembly file for the Bootrom, and I think last week we took a look and we started from the beginning, and we had those vectors, and the first entry is, I think, the stack pointer, if I'm not mistaken. I think there was like we did this last vector table last week and found the information. Yeah, so offset 0 is ASCII main, the stack pointer, and then there is like the exceptions, and I think there was at some point a list of the exceptions. Yep. So exception number 1 is reset. So basically that's what's running when the system is booting. So that's the reset address. And then I think I explained that the highest bit is the lowest bit. The LSB is always set because that's thumb mode. So we went to address ED 0000 E. Where was that? Let's make the font larger. Not that big. Yep. So not ED, EE. That was the problem. Yeah, and we found the start method, and then we found the source code of the same method. So there is the Pico Bootrom. It's open source, so we can read the source code and not just the compiled just the assembly code. But here the source code is assembly code. The only benefit is that now we have comments, so we can understand why they are doing whatever we see here. So okay, I think let's start with just loading this Bootrom into the memory, and then try to figure out how we work our way from there. So let's add another bootrom.hacks, not Bootrom, bootrom.hacks. And where is that bootrom.hacks? Do we even get a hex file for it, or how does it work here? Yeah, I think there is no hex file. So what's in the build? Oh, there is a hex and H32. Interesting. Probably just yeah, all the just a sequence of 32-bit so D words with the contents. I can recognize like this these vectors here, like the this number and then this one. So yeah, but we already have like a way to load hex files. So let's just copy the hex file from here to here, and then let's change the code to also load that hex file. So right now we initialize the code by giving the constructor the hex file that we want to load. And since the Bootrom is pretty constant, I guess we don't need to give it as a constructor parameter. Actually, I think we can make it, instead of loading it from a file, we can just, let's ditch that idea. We can just load it, make it a constant Bootrom. And for that, we can actually use this pretty nicely formatted hex file, like dword file. So let's just add bootrom.ts and export bootrom equals new uint32 array, and then just all those numbers. And since this is JavaScript, we need to prefix them, and I can use this nice keyboard shortcut Ctrl+Shift+L to just select all these numbers that I have in this file, and then I can add 0x and a comma to make it a valid initializer for this array. Oh, and that's export const. And that's it. We got the Bootrom in TypeScript. Oh, just this one is redundant. Okay, cool. So yeah, let's just double check BE00, and that should also be the latest. Yeah, this is the end, my old friend, the end. Okay, nice. They have some humor there, a nice sense of humor. Let's look if they have some funny comment. No, they don't have any funny comments here. Okay, cool. Anyway, so now we have the Bootrom, and we can import it. Import Bootrom from Bootrom, and then we can start respecting or reading data and flash like instructions from the Bootrom. So in order to do that, we had all those read methods. So now we have this to do. We can implement it. We should be reading it from the Bootrom if it's below the flash start address. So basically, if it's less than bootrom.length, then just read it from Bootrom. And the Bootrom is just an unsigned int array. We need to divide the address by 4 because each element in this array is 4 bytes and the address is a byte address. And voila, we have some failing tests. And I think the reason for that is we actually, in the tests, we actually assume that the code loads at address 0. So now all the tests fail. Great, great assumption. So what we're going to do, probably just fix that. I think that would be the right thing to do. So it will take a short while, but let's change all of these friends to it's equal to the flash start address. I think that was 10 million. And hooray, already most of the tests pass, but there are a few tests that actually rely on the value of PC, like this one. Oh, this one also initializes it differently, so let's fix those two. And then, yeah, 2 and 2 and 14 is D? E. Yep. Okay. And then what do we have here? Yep. +2 and also +2. Cool. And +2 as well. And the last one, same trick. Okay, test spacing again. Whew. And now we have code that loads the Bootrom into the memory, and we already have the Bootrom, but we still can't read instructions from the Bootrom. Oh, I think we can, because we are using readUint, which uses this method. So I think we are ready to execute the Bootrom and see what happens. Now we need to sort of boot the microcontroller, and by booting the microcontroller, I just mean looking at this vector table that we have here and loading this value into ASCII and this value into PC. So let's create a method for that and call it boot. Or you know what? We can actually do it in the constructor because it makes sense. We already initialize ASCII and we chose some arbitrary value which is not too far from the actual value, which is nice. Basically, I think we use the RAM size of the RP2040 to determine that. So we can just do its Bootrom location 0, and this.pc gets Bootrom location 1, right? That's the second D word. Cool. At this point, the Pico emulator should boot properly. I think if we start a program again, it will, yeah, it still runs because we override PC here, but let's see what happens if we don't, if we just start executing. Let's do 10 first instructions and let's see what happens. Okay, nothing happens, probably because those instructions are already recognized or I don't know what. Let's just print the PC to string 16 to see what it's actually doing. Yep. So you see it's starting from EF, which is the start address, and it's running all those instructions until 101. So let's go there. All right. We should start from EE, not from EF. So we have we should when we initialize PC, we should clear the lowermost bit. So that would be yeah, that would clear the lowermost bit. And let's start again. And yeah, now it starts from EE, and now we are getting like some instructions that are not implemented and reading from places in memory, which makes more sense for like arbitrary sequence of instructions. So actually let's add a unit test for that, just for the sake of it. Where are we? Yep. So basically it should initialize PC and SP according to Bootrom. Yeah, just use this kind of string so I can use apostrophes here. Bootrom vector table, and then I just create a new instance, and I can assert that expect rp2040.sp to equal. I probably should have done this before going ahead and just running the test program, but I already did, and I found a bug with the and PC, the bug with the LSB bit, just by doing that. So it should be EE. Okay, perfect. We have a test case and it passes. And let's see what's at F8. What's missing at F8? Why can't we boot? So we have F8. Or, yeah, that was F8. What's at F6? Maybe the problem is, oh, it's without the zeros. And yeah, this is F6, right? So F6 and F8 is just a part of, it's a part of BL. So why do we get this print? It should have skipped that instruction as far as I can remember. We just didn't implement BL, so let's check this out. And it doesn't print BL ignored. Wow. So something must be wrong if it doesn't recognize this instruction. Yeah, let's go to the instruction manual and see what's the encoding for BL and what we are doing wrong here. Do we have any unit tests for that? Not really. So let's create a unit test for that first, because it might be a good time to implement BL. Let's BL. What was that? We had F8, that was BL34, whatever. BL34 instruction. Cool. And then we have this opcode BL and 34. And I think we expect the PC after that to just equal to this value, probably 34, because we go to number 34. And then there is also, I think, BL affects the link register, but let's just consult the manual about that. Manual. So where is BL? Instruction details. BL, where are you? Branch with leak, immediate, calls a subroutine. So it has those, and IMM, and what is J1 and J2? There are probably a few variants of this. All right, so anyway, it takes PC, and then LR is the value of PC with the LSB set to 1, and then it just goes to PC plus the immediate, so it's relative branch. So it should be this plus 24. Let's do it hexa, that would be easier. Yep. Okay, and then we expect the link register to contain PC, and I think, if I'm not mistaken, that means PC plus 4. Like the I think we spoke about that last time. Like wherever we want to read from PC, it's actually really inside an instruction. We actually need to look at to add 4 to the current value. And we have the test case. Let's implement the assembler for that. So opcode BL, export function opcode BL, and it gets an IMM 32, right? So yeah, it gets 2 IMMs, but yeah, let's just go with IMM because it's a single address, which is, oh, what is I1, I2? There is S, which is this bit. Okay, and then I1. Ooh, yeah, there is some logic here. So there are a few bits, J1 and J2, which are okay. Let's just copy it to the code and then figure out what to do with that. But so we have okay, so we have the lowest bit is always ignored, basically. We don't look at it. So we take the next IMM11 is just like the next, the second, like after stripping from IMM 1 bit, we take the next 11 bits, so that would be 11 bits. That's 2. Yeah, 7FF. FF is 8 bits, and then 9, 10, 11. Yeah, that sounds about right. And then we need to take the next 10 bits from this byte. So, we need to, so the next 10 bits, so that would be IMM10 is just IMM shift 12 %. And then we need 10 bits, so that's 3FF. Okay, and now we can use that probably to encode the instruction. And now we need to decide about I1 and I2. So I1 is J1 XOR and I2. Okay, so basically we can say that J1 is, they call it, no, it's first J2, then J1. J1 is IMM. What is 34 hex? Never mind. Kevin, you say that you are lost. Where have you? Where did you lose me? Let me know. Anyway, so the next bit is the next bit of the number. That's J2. Is just I'm taking this next bit and I am XORing it with the sign bit. So let's have the sign bit first. So basically, if IMM is greater than 0, it's 0, otherwise it's 1. Or maybe if it's less than 0, then this is going to be 1, a negative number, otherwise 0. And then J2, that's the next bit from the number. So that would be, we had 22, and then we take that bit, and I'm probably making errors here, so let me know. And by the way, hi Stepko, let me know if you spot any error, because I'm probably making some, and that's that should be XORed with the sign bit, and then J2 is just the same with the next bit. Not sure why they did it like that, but whatever. Okay, so total of 24 bits of addressable space, I guess. And then finally we can use that. So we can use that to build the instruction. So we need to return a 32-bit integer, which is all those. Tony is asking why just not use binary. Use binary for what? I'm not sure how you would use binary there. And what I'm trying to do is just, to take this number, this label, which is a number in this range, and then encoding it to this format. So 0B 11110 that would be shifted by a lot, 16 plus 11, that's 27, and then yeah, that's the first part. And then we have the sign bit shifted by 26, and then we have that's IMM10 shifted by 16. Oh, so for IMM11, we need a shift because they eventually add this 0 at the end. So I think we need to reverse that. Like they exclude the they remove the least significant bit when the instruction is encoded. And I think that's why we have this 24 bit range, even though we use just 23 bits, 10 plus 11 plus 1 plus 1, 23 bits to encode the address. So they just save on space and they remove that bit when they encode this instruction. But thanks for the comments. Oh, for masking the fields, yeah, we could use bits, yeah. Okay, so IMM10, and we have then FS0B11 shifted by 14, and then we have J1 shifted by 13, J1, not J13. Wow, that's the longest instruction in the manual. We can actually do something like this and just encode those two together, and then J2 shifted. Yeah, we could probably do that, like joining I1 and I2, even though they appear at different locations, so in the encoded instructions, so I don't know. So J2 by 11, and finally I think one thing that probably confuses you, we are encoding, so we are basically taking this and building this, and not the other way around. When we get to implementing the instruction, which will be in a moment, then we'll do the reverse process. We'll have this and we'll need to construct this. And then it will probably make more sense to, we won't need to apply any shift here because it's just take those bits and those we'll be able to join them together. But right now we are doing the opposite process, and I think that's something that might be confusing. Anyway, I think it's good. Let's test it. So let's assembler spec. Let's drag it to this window, and then we can check the BL encoder. And yeah, if we hadn't embarked on the adventure to build our own assembler, we could have skipped that part, but what's the fun in that? Anyway, so we have this example that this one encodes BL34. And is that like 34? Is that an absolute address? Yep. So this is, let's find one which is easier to, okay, no, let's do that one. So BL, it's not BL34, it's actually BL to current instruction, like this one, minus 34. So let's see, how would that be? So F6. Yeah, everybody was in decoding, and I was in encoding. That explains. 34. So yeah, that's the offset. So whatever. we don't need this number anymore. So BL, we go minus, we go this amount of places backward, and then we expect the encoding of that 24. No, actually, it's relative to the next instruction. So in this case, that's what the instruction will be written in assembly. I'm not sure. Let's just let's just assume that it's written the same way it's encoded, but we are going this minus 34, not this minus 34. And then the encoding should be this gigantic number. Okay. And obviously we got the wrong result. Let's see why. Yeah, expected, received. So first of all, we need to convert it to a signed number, or maybe we need to convert this to unsigned number. Let's convert the result to unsigned number. So I think in JavaScript, the way to convert, there is a trick to convert unsigned JavaScript. Like to convert to signed, we have this or 0, and I think there is an equivalent way to convert maybe here. Yeah, I'm not sure. Okay, I think that's, yeah, we could use a uint array, but I think that I've seen that operator, that shift operator in the past. I think it's shift without regards to sign. Let's make it, it's getting out of control. So let's return opcode and then shift it. Okay, so now we still, 3. Okay, so now we get a positive number, but there are some bits that are wrong. Let's print the result in hexa just to see what's the difference. Okay, so we have F7, FFD, 70, 90. So these D7 are wrong. Where are these D7 coming? Where is this coming from? I suspect this might be either J1, J2, or IMM11. So first of all, let's check if sign is set correctly. Yes, it is, because the number is positive. It's negative, so we expect it to be 1. And let's see if this number, let's copy it. I can't copy it. Okay. Okay, let's just write it down. It's to say basically 7 and D here instead of what we expect. So which bit are those? 7 and D. It seems like if this is 7, so this is going, this is working correctly, this IMM11, and then the next few bits are these J1, J2, and this mask. If it's 8, then I think J1 and J2, J1. Oh, why is it shifted by 1? I think that should have been 11. And do we get anything different now? Okay, not really. It's the same number, right? So we sort of found a bug, but it's still not working as we expected. There are still missing bits here. Select J1 and J2. So both are 0, but they should be 1. Why is that 0? Let's see what this returns. Interesting. Why is shifting it this value %1? Yeah, making simulator is hard. That's right, Stopco. Okay, so let's see. Oh, yeah, I forgot. It's not. So we need to not those. Oh, that was my bad. I just didn't realize it was not. So not is just 1 minus. So 1 to 0 or 0 to 1, and test passes. Yeah, congratulations. Let's just do another one, this time with positive, just to see that we are encoding it correctly, because the next step would be to use that in the test for the opcode, so we don't want to be confused by that. So let's just look for another branch which is going forward. These all are going back, but there must be one that goes forward. Maybe not in the Bootrom though. Maybe in the UR there is. Or you know what? The best way to look for them is in the beginning. They are most likely to exist. Okay. Where is the next? BL. Okay, BL44. That sounds good. So 44, and we are in 30A, so that would be 30A 10. So that's just we don't want this terminal anymore. Goodbye. So that would be just the encoding of jumping 10 addresses forward. So that's BL plus 10, and we expect the encoding of it to equal this magical number, and it works perfect. So now with this amazing encoder of the BL instructions, we can start writing the test. Oh, we already did. So great. So we can start implementing the test. And it doesn't really matter. Yeah, I think. Okay, so one thing I can already spot, it should jump to 38, because if we are starting from 0 and then we are jumping relative to PC plus 4, then the result would be 38. And now we can go on and implement the branch link, yep, and figure out why it doesn't even decode it correctly. So we are looking at opcode, and that should be 11110. And then there is opcode 2 that should be 11. Okay, so first of all, I see that we are not even looking at this bit. We missed it when we wrote this opcode checking. So let's do it. Oh, and I suspect that there is something wrong with the way we calculate opcode 2. For instance, we are reading it from the wrong address, because we need to read from the next PC. And yeah, let's print them and see if they make sense. And just focus on this test, so we won't be confused by the next things. Tests. Where are we? BL. Okay, so this is opcode to string 16, and then we have opcode 2. It's all Fs, and is that the actual encoding for the string 16 for the opcode? Nope, we are doing something wrong here. Why does this not return? Maybe this is broken. Read uint34 address, and how does that work? Yep. So yes, so here we sort of assumed that we get the addresses aligned, but then in read uint16 we sort of broke that assumption. So that's a problem. There are a few ways to fix that. I think we'll just fix uint, read uint 16 and read uint 8 to just use aligned address always. So we need, in order to align the address, we just need to clear the lower 2 bits. So that would be 1, 2, 3, 4, 5, 6, 7, and then not F, not E, not this C. So clearing, oh, we actually need to clear, yeah, and here. And then we need to decide which half word we want based on the we can also, so yeah, we can also decide that read uint, let's comment this, we assume that address is aligned. And then here, we also assume that the address is aligned, and this will make our life simpler. And then if address and so if this the second LSB is set, will return the highest byte because we are big endian. Otherwise, we'll return the lower not byte, half word. And then we can do the same thing with this one, just FE, and then check the next bit. So address and 1, then value and the high byte, otherwise the low byte. Cool. So now read uint 16 should probably 16-bit, and that's 32-bit aligned. Okay. Now we should probably be getting the correct opcode. Let's focus. Yeah. That should be F. Let's again convert it to unsigned. But yeah, before. That's interesting. Oh, yeah. We should also do a shift here. So shifting this by 16, or here we should shift by 8 to get it correct. And yeah, and we also want this to be unsigned because it's read unsigned int. So we'll use this trick to make it unsigned. Maybe I should turn this into a function to make it more readable. Maybe not. I don't know yet. We'll see about that. All right, and now, yeah, it seems almost correct. This one is correct. This is the low byte, and this one is strange. Let's see what's going on here. So let's print address. Yeah, the addresses look fine. And then let's print, let's also print next to each address the value to see that we are reading the same value. And yep, so we are reading the right thing. And then the only question is, why does this not return the high byte? And that would be Maybe we need another set of parentheses here. Okay, I think the thing is, all right, yeah. That's my bad. I think the problem was we need to use this shift operator instead of using the standard shift operator in order not to fill it with once when we shift right. Let's see if I was correct about this. Yep, now it returns the why does it return the low byte though? We want it to return the high byte and not the low byte. So what's wrong with that? Oh yeah, sure. We should do the bitwise end and then do the shift. Okay. So now let's see. What did we get? What is going on here? Okay. So now all F's, which is still not what we want to get. This and this. Okay, let's print it without a shift. So shift 0. Why is it all F's? What's the value of, what do we get in value? Okay, so interesting. For some reason they are all F's in the high bytes. And are we reading? We should be reading from the correct place, right? That's where we are reading from. And let's print this value and double check. Wow, what's going on here? Flash 6. Oh, right. I got it. So the test is doing the wrong thing. It's writing 32 bits integer into this array, which is a uint16 array. So it's just writing 1 byte. Yeah, let's just create flash 32 for this purpose. Or we can just use the data view, which lets us, I mean, this is the only instruction that is 32. So just set uint 32 and the byte offset should be 0 and this should be the value. Okay, and now, yeah, now we get values that start to make sense, I guess. Let's double check that. Focusing on this test, and now opcode 2 should be anyway unsigned, but oh yeah, we get the wrong value. You see, it's like the lowest half word with the byte swap, because when we set uint 32, we should tell it it's Little Indian. And now finally the opcode is decoded correctly, the 2-byte opcode of BL. So we can remove all those debug prints. And hopefully we will end in this, yeah, no, not yet. Hopefully we wanted to get into this if statement, but that didn't happen. So let's figure out why. 0, 0, 0. Yeah, let's keep the print for the opcode for the time being. So yeah, so oh, wait a moment. Opcode should be the lower part, so it should be this. Yeah, that's the lower byte, and then opcode 2 should be the higher byte. So I think our logic for matching them is not correct, because opcode should be the lower byte, so this should be opcode. Okay, so let's change the logic for matching them. So we should check these bits in opcode, so that's and these bits in opcode 2, so that should be opcode 2, the higher byte. We want it to match this pattern, and then the lower byte should match. And now we hit the if, but we already spotted that we are missing one bit that we should check. So opcode, that would be, if that's 14, that's 12%. So now we are finally doing the decoding. If that's equal 1. Yep. Ooh, that's long. So we still match, and now we can start decoding the part. So let's start. Im11 is just like the 11. That's the lower byte, so that's opcode. We have 7FF. I have this cache in my mind, and then we have J2. It's just opcode shifted by 11. No, by 10, or by 11. So yeah, perfect. Oh, somebody is sharing their Python decoding address, but ignoring the INJ stuff. We need them, but anyway, thanks for sharing them. Is that the person who told me is working on a Python emulator for this chip? If so, it's really cool. Anyway, so J1 is 2 bits away, so J2. And then we only need IMM10 and the sign. IMM10, not in Hebrew, so that would be from opcode 2, taking just 10 bits, and that's J1, not J2. And we need a sign. So sign, we take 10. So shifted by 10, and we take a bit. And finally, we can reconstruct the new value of PC, and instead of just adding 2, which is just skipping the instruction, we need to add 2 plus, how do we call this here? IMM32. And IMM32 is, let's see, so that's IMM10, no, IMM11 shifted left by 1, and then actually, okay, and then the next is IMM10 shifted by 12, so 11 plus 1. And then we also, IMM10, need to do, we have I2 and I1. Let's just copy them. Const I1, 1 minus SR J1, and same goes for I2, minus this. Huh? No, that's not what I mean. Yep. Yes, that's better. And then we have next is I2 and I1. So I2 by 22, I1 by 33, and then we need to do the sign bit as well. So yeah, we don't need this ignore anymore. Oh, and we also need to update LR to this.pc +2 and +2 because we already updated PC. We added 2 at the beginning. We did this last time, and the test passes. And the reason it passes is because this is a jump forward. So we didn't take care of the sign, but since this is a positive number, then it passes. Let's create another test case for the negative case. And yeah, 32 hexa, just for the sake of completeness. And let's go, let's say, -10 hexa. And yeah, we can start with, you know, -10 hexa. That should be the result. And the opcode would be just -10 hexa. Yeah, and now we get a wrong value because we ignore the sign. If we focus on this test, we can see that the IMM32 is not what we expected. Console.log is not what we expect it to be, obviously, because it's signed. So we can probably just use the sign bit, so S31, and then since we are doing the bitwise ORs, it should probably take it as a sign, but let's see if it does the right thing. Oh, almost. Maybe we should just put all of this in parentheses. Does it help? No, that didn't make any difference. So why did it not give us the result we expected? -7f, and without a sign, that's, oh yeah, we should set all the remaining bits to 1, I guess, if it's negative. So yeah, we just need to do So if we have a sign, then we want to set 1, 2, 3, 4, 5, 6, otherwise just 0, and shift it by 24, and that should be 7, I guess. 8. Yep. Yeah, so that's how you code. You just try until you hit the right number. And cool. So still doesn't pass though, even though we have 10, -10. But the reason is that we expect it to be this value. So PC +4, we forgot to account for it in the test. Anyway, pretty cryptic code, but the good thing about this code is once it works, nobody ever needs to touch it. And I can tell you from my experience with the AVR simulator, you just write it once, it works, and you forget about it, hopefully. Yeah, and there is a note from Tony about readability. So right now I probably prefer readability over making it faster, because we can always optimize later. But I don't know, just when writing this kind of code, it's easier for me to like write it this way, but probably to make it more readable to other people than using something like we'll copy it from the chat. So Tony wrote it this way. It's probably more readable. So sorry about not doing that until now. And thanks, Tony, for sharing your code. He just shared another piece, so that's how he decoded it. For some reason he used the sign a bit differently, not sure why. Yeah, now it makes more sense because then he signs extends it, so that makes more sense. So Tony, if you want to add J1 and J2 to the simulator, you now know how to calculate them. That shouldn't be too hard. I guess that would be just this one would go to 24, and then you need to do something like so you have these bits, so so that's probably, why do you take 14 bits, or is that the offset? Anyway, you will figure it out. Okay, so we got this BL instruction, and we can go back to running the Bootrom code, and let's see what happens. So, oh yeah, you can see that it got to F4 and then it jumped to this address. Let's see if that, oh, read from invalid memory address. Okay, let's go to the disassembled code and see if that makes any sense. Let's open it. Let's copy it here in new tab, so we won't need to go back and forth. And let's see what happens here. So we start with EE, which makes sense. And then we read from invalid memory address, which may make sense or not. And then we go to F0, F2, F4, and F4 is branching to 136, and it seems like we branched to the right location. And then we are reading, and we have some handshake loop. Anyway, it seems like we have all the instructions we need up to this point, so let's just save this file. Let's keep running it. A few more instructions, so instead of 10 instructions, let's run 20 and cross fingers to see if we're missing anything. And yes, another instruction that we are missing, which is LSRS. I think we implemented something like that. It sounds familiar. LSRS. No, we haven't. What's LSRS? We probably did something similar. Logic shift right, and we probably did LS. Yeah. So let's do LSRS. It shouldn't take too long, probably, because we already have this LSRS, but you never know. LSRS. So LSLS. And let's do LSRS. In this case, we have LSRS R1. So let's do LSRS R111. LSRS, and let's create an encoder for it, because we really LSRS R1, because we really miss creating these kind of encoders. And then we put some value in, so that's shift right. So put this value, and we expect, we don't need all this long chain. We can just put this and expect the result to be this, and that should be R1. And while at it, let's change this to use R5 and this one as well, just for the sake of readability. And yeah, and there is no carry. I don't know if this instruction even has carry. Let's check it out. So let's create an encoder. So that's LSRS. How does that work? LSRS is something seemingly wrong in the disassembly. How is that? Let's see. 0001 anyway, we need to implement it nevertheless. So let's do it and see what happens there. Yeah, what? Huh? Yeah, Tony is saying in the chat that where did you see FCE? Tony is saying that this is a wrong disassembly, but I'm not sure. You're talking about something about FCE. Don't see any FCE here. Anyway, till Tony explains what he means, let's just write the encoder for that. It should be a piece of cake compared to what we did up to now. So to the previous one, to the BL one. So that's, and then we have IMM5, which somebody already did, RM and RD. Or no, in the instruction it comes RD, then RM. So RD, RM, IMM5, RD, RM, IMM5, and then we have IMM5, RM, RD, IMM5, RM, and RD. 3 bits, 3 bits, 6 bits. No, 5 bits. 3, 3, 5, 3, 3, 5. Okay, so we have the decoder, and okay, later. Cool. Okay, and let's just create a test case for that real quick. So assembler spec, LSRS, and that was it here. So LSRS R1 should equal this. LSRS opcode LSRS, and yeah, hexa. Yeah, it passes. Okay, that was easy compared to the BL. Okay, and then we have what's the code IMM shift? Interesting. 0, 1. So if IMM is 0, then we shift by 32. What does shifting by 32 means? Just clearing it, I guess. Okay, interesting. So that's shift T, LSR, and then shift L, okay, and shift T and shift N, and that was LS, LS, LLLL, LSR, right? So the code shift, and then this is doing the shift. Okay. Shift with carry, so probably 32. Shifting 0 will probably shift the register, but to do something with the carry. Okay, so where is the spec file? Yeah, I think that's Tony is asking about clearing. I think that's what they mean by shifting by 32 and then probably copying one of the bits into the carry. We'll look into that in a moment. RP2040 spec. So we have the opcode, and then yeah, probably shifting the MSP into carry or something like that. Okay, and then let's do another test case for the 0. So 0 should basically clear the register, I guess. So no, not the PC. This one should be all ones, and then we expect it to be 0 if this is 0. And I guess carry would be true, but let's see what shift ASPR.C, what shift C does with shift type LSR and shift N, which is 32. So shift C LSR result carry out LSRC and LSRC. Yeah, I think this means that in any case, like the 0 extend, it's what is extended X? It's adding shift plus N zeros, I guess, to the left of X of the number, and then yeah, we are taking shifts plus N minus two shifts, shift minus 1. Yeah, so it's the last bit that was shifted, that's the carry. So yeah, so if I'm not mistaken, this means that carry should be 1 because the last bit was 1 here. All of them were 1, but the MSB was 1. And then here we actually shifted out this 0, so carry should be false. Okay, so we have the test cases, and now let's implement the instruction. So we have this one, LSLS, and we have LSLR. And LSLR, what was it? We need to check, no, LSR immediate, yep. We need to check if this is the opcode immediate. Okay, so this is the opcode 00001, and then we have IMM5, RM, and RD. It's the same decoding as the LSLS. And then we do this. If IMM5, then the result is this, otherwise the result is this. And so this should probably be passing already, or no? Why not? Oh, yeah, shift right. And then yeah, let's just make sure that this is what I think this is doing, like shift right without regards to sign. Yeah, unsigned right shift, so it always feels 0, so good. That's the shift that we are interested in. And then okay, so yeah, so the only problem is with the carry, and here it should actually be false, right? Because we didn't have carry, but here it should be true. And then the carry should be okay, so it should be, why is it not sure. Anyway, it should just be the bit that was, yeah, so we should just shift by IMM5 minus 1 and take that single bit that was the last bit that we dropped. Otherwise, if this is 0, it just like or we can make it, write it differently. So if IMM5, then IMM5 minus 1. Otherwise, it just 31-bit shift. So we take the MSB in this case, and yeah, and we need to convert it to Boolean because this is a number. So this is one way to convert, and it's happy. But we still haven't. I think this is okay, but let's just double check that this also updates. Yep, n is this bit and this is 0 bit. Cool. So we have LSLR. Let's run this again and see if it's happy. Yep, it's happy. And let's continue running a few more instructions and see what happens. It seems like we are in some kind of a loop. Let's check what this loop does. That would be going back to this, and that's 140. So time to actually understand what this code is doing. So core 0 handshake loop is loading some value, reading something from the memory. Let's try to find the source code for this. Maybe it explains something. Wait for vector, that's what we are doing. So it's reading from SD FIFO FDRD offset. LDR. Yeah. So this is like, it's going here. So it's reading a value. It's reading another value. So it's trying to drain some kind of FIFO. Anyway, we can probably skip all this initialization code and just I'm not sure if there is anything that we need. We might be beaten by this, but right now it doesn't seem like the perfect approach to me to just, you know, go and simulate everything that this code expects to happen in the microcontroller, because that could take a long time. It's doing some kind of I remember from last week that it has this what was that, Bootrom. It has this so I think we passed which core I am, and then I'm not sure where we are here in this flowchart, but we want to get into this one, into enter flash second stage. So let's just take a look at the code and see what it does. So we have this, we are right now inside wait for vector. So yes, so we started with start. We then did this checking with, or are we in wait for vector? Yes, yes we did. We are. Yeah, so I think we got into the wrong place, because this code checks if this is core 0 and go to holding pen if not. And if I understand correctly, it went to that place. Let's see. Yeah, F4 is like F4. Yeah, it's taking the branch, right? 136. Yeah, it took the branch. So it actually read some value and it expected it to be 0, but it wasn't. So that's SAO base plus SAO CPID offset, which is 0 from SAO base. What's SAO base? Yeah, this address. So yeah, and it tells us. So this address seems to contain the current ID of the CPU. Let's just double check it in the datasheet. IO port registers, SAO base, and that was CPU ID offset, I think. What? Where were we? SAO base. Huh? Not sure I got it. Okay, SAO CPID offset. Yeah, is the first register. Yeah, we can see this is the first register, value 0 when reading from processor core 0 and 1 when read from processor core 1. So I think it would make sense to implement this anyway. We are not going to support multi-core, but at least if some code want to know which core it's currently running on, we do want it to return the right value. I think right now reads from invalid memory addresses return -1. So what we're going to do, we are just going to implement like another memory hook, this dot read hooks, and this address, which is SAO base. And this will probably move into another file at some point, which will implement this SAO. Oh, we already have this constant plus SAO CPU ID offset, which is just 0. So we'll probably have, not SSL, we'll probably have a different module which will handle this in the future. But for now, let's just take care of this specific address. Oh, this is a map, right? Dot set. So set this read hook into this function that always returns. Can actually, no, I want to write it like this because I want to explain what this is. Returns the current CPU core ID. Always 0 for now. Okay, cool. And why do the tests fail? Huh? We are doing LDRB here and it gets 0. Where does it read from? It reads from R4. And do we have a bug in the test? It reads from R4, but we didn't initialize R4. So I think there is an issue here. Did we change this code or something like that? Because that was LDRB. No, probably had a bug in the test which we have just uncovered for just some mysterious reason. Yeah, okay, so I guess R4 is where we expect to see the value. So what is going on here? Did we use the incorrect address here or something like that? Let's just focus on this test for a moment. Okay, and it doesn't get into the read hook. So what happens here? We are reading from this SRAM here. So what's going on here? LDRB. We are reading from, no idea how we get into this. It seems to be reading from the, maybe fixing read uint 8 is the culprit. It returns 0. Reading from, so it's load B from, it should return 66. Let's see what value we get here. 6600. And what address do we have here? The address is the high, and so it should be 0 0 because this is little Indian. Oh yeah, the same issue that we have here. We should first end and then do the shift. So we are so lucky to, and yeah, triple shift just for the good measures. We are so lucky to have these tests. We just code a bug we introduced by rewriting these functions, and otherwise it would probably have gone unnoticed, and we would lose sweat over finding why something suddenly breaks. So thank you, unit tests. Anyway, let's go back. We can remove the filter. Let's go back to the microcontroller. So now if we run the Bootrom again, it should take a different path, and you can see it takes a different path. It actually goes to a different function, and it seems to correctly return from it, which is quite interesting. And or maybe not. Let's see what's there. 100. No, that was 100 exa. Yep. Goes to check. So yeah, let's see what happened here. Huh? Why isn't it implemented to it? We just implemented BL. We worked really hard to implement BL. What happened? Okay. Instruction at F6. That's BL. It should have not continued executing a code. It should have branched to NMI. Where is NMI? 34. Somehow it does branch later or go to, oh, that goes to 30 dead. Yeah. It's dead. Anyway, let's check what's wrong with the implementation of BL. Let's do it like that. Let's run it just so it gets to the BL. Then print the values of the opcodes and see if they make sense. Code. So this should be the low byte and this should be the high byte. And compare it to what we have here. Oh, this is the first one, this is the second one. So why isn't it decoded correctly? BL. Yeah, let's print those values. Maybe I got it all wrong somehow. Console.log. So maybe both encoding and decoding are wrong. That could be the case, even though we had a test case to check this. But then, yeah. Okay. The first one is false, so opcode 2. These bits, this doesn't match. Okay, and we expect opcode 2. That's to be the high byte, right? FF9D. So, yeah, FF is definitely not starting with 1110, starting with all ones, which is quite strange. I think for some reason the bytes are reversed in memory than what we assumed, so we have to fix the encoding and the decoding. So basically, where is the assembler spec? branch BL giving us so much trouble? So we thought, I think this one came from here. Yeah, we thought it's written this way, but it's probably big Indian, so it's probably this, and this one is probably this. But yeah, before I change the tests, let's just first see if it works with the actual code, which is like the most important test. So basically I want to change all the opcode to here into opcode. No, let's do it the other way around. It will be easier because there are way more opcodes than opcode 2. So that would be opcode 2. And then this one is opcode and opcode. Now it doesn't decode, but here I guess it would decode correctly. Yeah, and let's just run it one more instruction to see if it jumps to the right place. And if it does, we need to fix the encoder as well. So 34, it goes to 34, and I think that's, yeah, it should have gone to 34. So now this is correct, at least according to the code. So we need to fix that. Okay, it shouldn't take too long. Let's first fix the tests assemblers, because that's easy. Just swapping this and this. And now, yeah, let's just swap this and this. So this is not shifted. This is 10. And then this is 11. And then this is 16. And then 16, 27. And then 29, right? And then this is like, huh? Ah, okay, 29, and this is 28. Okay, and it passes, yay! We fixed the assembler as well. Okay, so let's see what's going on now. I mean, we already know it works. Let's remove this debug prints. And I think we have a few more inside BL, or don't we? Oh, yeah, that's the instruction that isn't implemented yet. What's there? 34. So 34 as move IP LR and IP. What's IP? So that's a move instruction. I think we have some kind of move. We have moves. So I think at that point I want to stop, like I told you before, stop doing the Bootrom, because I think that's a pretty deep rabbit hole and we don't really need all those peripherals that it takes care of at the moment. It's already loaded into the memory. Steve says that IP is PC, but I'm not entirely sure about that. Let's see if there is anything about IP register. There is. Huh? Okay, so there is someone that says that R12 is IP. Yeah, intra procedure call register. Yeah, it makes sense that it would be instruction pointer. That's how it's in x38, but apparently it's like IPS PLRPC. It's R12, and R11 is also FP, and R10 is also SL. I didn't know that. Yeah, you always learn something new. Anyway, thanks Tony for providing the answer to that in the chat, and yep, cool. But yeah, I think at this point we are going to stop worrying about this code in the Bootrom for now and just sort of see what it does. So how it gets into this point where it enters the flash second stage, and we'll just skip all the stuff until that point, unless we found something that we actually need, like if we see that it initializes some kind of data structure or something like that. Okay, so we have this start. Let's look at the why look at the disassembly when we have the source code. We have this start. It checks if we are core 0, otherwise it does something with NMI, and it should enable cloaks, and then it does something like check rescue. And if rescue is good, it goes here. 1F means to label 1 forward. And then it does check watchdog, probably, blah, 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 blah. And eventually it proceeds to the main flash pull boot sequence. This return, we continue BLX R3. So probably load something into R3 and then goes there, and then it goes to main. So I think main is the interesting part. Not sure about the question, Tony, but all these files, like if you are talking about these files, they can be found on GitHub. So it's just like GitHub Raspberry Pi Bootrom. So this is like the source code of the Bootrom, and you can just I think, yeah, we have the instructions to build it here. It's like 5 minutes of running these instructions. But if you need this file or something, just let me know and I will send it to you. Anyway, so it goes to main, and main is probably in a different file. Yeah, we can see main in the disassembly here. Yeah, so let's see if we can find the Pico Bootrom main. Okay, Bootrom main.c sounds promising. Yeah, so okay, let's go to main and let's see. It calls reset block, unreset block. It checks if we are running on the FPGA. Yeah. Okay, I think they used FPGA for development, so it's probably some hack for their FPGA chip. And then check CSN strap. What is CSN? CSN. CSN. Chip select. Okay, that's probably something it's doing to check with the flash. Anyway, it checks if sum is greater than 5, it goes to flash boot, otherwise it goes to USB boot. And we are interested in booting from flash. So let's see what flash boot does. Connect internal flash exit XAP. Then it has this loop that goes up to flash max attempts. So that's 128. So and then it tries to read something from the flash and CRC. And I think I've seen this described here. So load this amount of bytes from flash, checksum pass, then enter the second. Otherwise, it goes in a loop, like incrementing those values. Probably this does the increment of those values, and there should have been a delay of 100 nanoseconds, which I don't see here. Anyway, so this is probably doing this part of the flowchart. Oh, read flash CSN, high flash boot, low USB device, and I think that's what we have seen in main. So it's reading CSN, which is probably this GPIO IN bit that it's reading from. And then if it's high, it's reading it up to 9 times. And then if more than 5 of them, 5 or more are high, it goes to the flash boot. Otherwise, which is low, it goes to the USB device, to the USB boot. So that's what it does. And then this flash boot has this, don't know about the SSI, probably one of these is the configuration of the SSI, and then this is this loop that checks if tries to load the bytes and checks if the checksum pass, and if attempt equals max, so the checksum didn't pass, we just go to the USB boot sequence. Otherwise, we go into the flash second stage. So we are flushing the cache. We are flushing the flash cache. And then we enter boot 2, thumb bit set. What is enter boot 2? So there is this boot 2 load and boot 2 exit. And let's look at the disassembly of this. It will be probably easy to find it, or maybe not. So it's somewhere inside flash boot. Do we have flash boot here? No. It must have been inlined. Oh, there is this flash cache just before. So yeah, and this is like return is probably going to USB boot, because that's the next thing that happens in main. So this is probably the equivalent of this code. And then add R51, and this is like boot 2 entry, move R7, which is probably boot 2 exit, so LR gets 0, and then we just branch to the value inside R5. So basically what this code does is just putting the value 0 inside LR, and it says something here about that. Exit point is passed in LR, we pass null, boot 2 provides default for this case, and addition performed inside whatever. Okay, so this basically just jumps to this boot 2 load, and boot 2 load is boot 2 base, and boot 2 base is just SRAM and minus boot 2 size bytes. So boot 2 size bytes is just the 256 last byte of the RAM, and we can see that this is there is code that reads from boot 2 flash offset into boot 2 load, so into this memory address, and it reads this number of bytes, so 256, and the offset that was 0. So we're basically doing loading 256 bytes from the flash, from address 0 in the flash, from the start of the flash, into this address, which is just boot to base SRAM and minus the size of this boot2, and we are loading it, and then we are jumping there. So I think we could probably just fake that. Where was that? Oh, not this project. Yeah, we can probably do something like so first of all, we had is putting 0 in LR, so MCU.LR is 0, and then we need to load 256 bytes from flash to the end of SRAM, so MCU.SRAM.set and MCU.SRAM.length minus 256. Oh, that was the offset. And we need to MCU.flash.slice. We just want to take 256 bytes. Let's call it boot2 size, just to have a few less magic numbers in the code. So yeah, boot2 size, and then that's okay. So MCU SRAM set, blah 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 blah. So we copy this, and then we need to jump there. So MCU.PC is just SRAM. We had a constant for the SRAM, I think. That was RAM start address. Why did I say SRAM? Did it mention SRAM here? Or yeah, it said SRAM. Okay, so plus MCU SRAM length minus boot2 size. Okay, so right now I'm just skipping the entire Bootrom. It's loaded, it's there in the memory, but we are not running all the initialization code. Hopefully we won't be too sorry about that later. And jumping right into boot2. Let's see how this goes. Let's just run 10 instructions and see if it does anything that makes sense. Okay. Yeah, it does something, but like it reads from something that seems like a legit, that seems like ASCII address, and that seems like a RAM address, so it might be good. And there is an instruction that isn't implemented. But then since boot0 is the first vector, the first page of the flash, and we are reading it from a low UART, then it's basically the first bytes of a low UART, and it should be like this, all these bytes, the instructions that it's running. So let's check the disassembly for a low UART, and yeah, we can see it has a disassembly of the section.txt, which starts from 256, and I think it doesn't have, yeah, it like has this boot section, which is at this address, like the start of the flash, and this is the right size, but for some reason they didn't dump it into this disassembly. So I think what we're going to do, we are just going to search for the source code of this boot2 inside the SDK. So let's look for boot2, and there are a few. Let's look just inside the Pico SDK, and there are a few boot stage 2 sounds promising. Let's close this other window for now. Okay, so we have this boot stage 2, which yeah, it looks like it loads on the top, okay, which is above the Bootrom stack. top 200. Yeah, it looks like this is the same address as we had here, so it looks like the correct thing. And that's the length, which is 256 minus 4 bytes for the checksum. And then there are like a few variations. I think we'll just go with the generic, probably different variations for different types of flash chips or something like that. Ooh, wow. Second stage boot. Wow, they surely invested in this ASCII art. Wow, I'm impressed. Things that you find when you dive into the code of the second stage boot of the Pi. So yeah, okay. Whoa, 219. So they have been working it for some time. Okay, so let's take a look at that. Stage 2 boot, push LR, and then a bunch of instructions. Okay. Yeah. So let's see what this does. It does push LR, so we expect the first instruction to be push LR. Let's see if this is the case. Let's just execute one instruction and put a const log in this push to see if it's inside push. And see if it gets into this. Yep. So I think let's double check. How do we know which registers? No, we won't do that. We just assume that this is push, and then the next instruction should be LDR. And we see that there is like after this, the second instruction reads from this address, and let's see what is XAP SSI base. XAP SSI base. LDR. This is not the same. Oh, wait a second. Did we look at the generic file or the other one? Yeah, that's the generic one. I wonder which one is being used. Maybe we can find it in the compiled low UART or in the make file to make sure we are looking at the right thing. That's inside the Pico examples build. That's low UART. Hello UART. Hello UART. Where are you? Inside UART, obviously. Maybe we have something here about boot 2. Not really. Maybe in the make file. Not. Yeah, it could be statically linked or like linked into some library that is used. This looks promising. Yeah, it's probably just copying this from somewhere. And that was boot 2. Okay, so let's do something else. Let's try to look for the name of this file. Nobody references it. Nowhere. Interesting. Then this one. Maybe without a boot 2. Okay. So maybe I would search for this one with the decorations. Okay, interesting. It appears referenced from here, but there was one other that was this one, maybe. Oh, that appears. If not, Pico default boot stage file. So that is the default one. Okay. So maybe that would be the right place to look for the instructions for the actual code. And here we load into R3 something different, which is this address. But it's still not what we are seeing. Is that the second instruction? Yes. Okay, interesting. What do we do here? Here we don't even have the push, so it can't be this one. And this one doesn't have the push as well. This one doesn't have the push as well, so only this one and this one start with push. I'm wondering why it reads from this memory address. Okay. Oh, probably I got it. It's loading into R3 this value, so this value is probably stored in this address. Okay, so but it's either this one or this one because we have the push at the beginning. Anyway, this one is a bit longer, I think, than the generic one, but it seems like this one is like the default for the SDK. So how can we verify that? Maybe by looking at the checksum. Is there like the checksum here somewhere, or no, they don't put a checksum. Let's see if there is. This instruction is move, and this one is also move. Yeah, I guess we'll just look at which value it loads into R3. So LDR, and then let's see which value it reads. 16. Okay. Oh, and we need to run 2 instructions to see the effect of that. Oh, that's probably the second LDR, because this is one that says where it's reading from. So let's see what it's reading from. Yeah, it's reading this value. Let's just make it a bit easier. Okay, so it's reading this value, and I think this is this, right? XAP, no, the other one. This pads QSPI base, right? Yep. So this seems like this is the right boot2 file. This is like what we have in those built-in examples, and let's see what it does. So it just loads a bunch of stuff. It doesn't, and saves a bunch of stuff. It doesn't do any kind of conditional. Disable SSI, set baud rate, some kind of configuration, probably for the flash or for this kind of flash or God knows what. Okay, so there are a few branches here. SSI ready. Self skip programming, dummy read. But the thing is, this is code. If we just want to have the simulator, the emulator generic, so it can take any hex file and just run it, we need to implement this because somebody may have a different boot code. So at least we need to do that. But it seems like after all this mumble jumble of like reading from the SPI or whatever, eventually it goes to soft reset, and soft reset jumps to XAP base, which is, I think, the start of the flash, right? Yep. Plus 101, and that's just right after the Bootrom. So well, basically the Bootrom just goes the stage just after the stage stage 2 boot, and this means that stage 2 boot just jumps right here into this reset start, the beginning of the code. So if we want to skip this for, you know what, yeah, I think we can skip this for now. We know that, or let's run it and see if it gets, maybe we are lucky and it just gets here anyway. So let's run it for like 200 instructions and see what happens if it actually jumps to where we want it to. Well, address offset is out of bounds. Okay, we have some out of bounds here. And we did get FA0. We did get some instruction running. The thing is, we don't have this disassembly with addresses, which makes it a bit yeah, Stepco is looking forward to test this. Cool. So we don't have the disassembly to debug this. So I'm thinking like going and making sure that all the instructions here are implemented without the disassembly, and I mean, those values look legit, I guess, but without the disassembly, figuring out why it gets out of bounds read. Probably something in the missing instructions is throwing it off, even though we only have one missing or two missing instructions, which is pretty impressive in my opinion. But let's just for now, let's just skip that part as well, and let's just pretend. So that's to start from boot 0, from boot 2, or how did we call it? Boot stage 2. And then just to start right after boot stage 2. So I'm cu.pc equals just, basically that's the address of the first instruction after boot stage 2. So again, we are sort of cheating our way and skipping the Bootrom and then the boot stage 2, but at least now we understand what we are skipping and what this code is doing, more or less. Like it seems like it's mostly initializing the flash and doing stuff with the SPI and the XAP bus, which are not really interesting in the simulation right now. And now we have the Bootrom loaded in memory and a few more instructions to work with. So let's see what happens when we run a low UART from the beginning. So low UART is running from here, and it should basically go to vector entry. Let's do it. Let's run it for like 10 instructions and see what happens. Okay, so 100, blah, 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 blah. Missing instruction. What's this missing instruction? LDMIA. Okay, and then we have another one, which is this MSR, I guess. Another 2-byte instruction. Okay. MSR. And then we have BX. Bunch of missing instructions. And then that doesn't really matter because we should have branched here, but don't we have LDR? Okay, probably don't, if it says doesn't know this instruction. Window, oh, yeah, that's that one. That one is fine. LDR is fine. So yeah, so we are missing those, I guess. 10 ACE 10 AC. Okay, there is no E, just 2-byte instruction, so it thinks this is an instruction, but it's not. So we are missing 3 instructions here just to get through this vector entry. So let's implement them. So instructions to implement. Let's write them down and start looking at them. So we need to implement this one, and this one. So what does LDMIA? It's probably loading data from this address into these registers or something like that. LDMIA. Load multiple increment after. Loads multiple registers from consecutive memory locations using an address from a base register. The sequential memory location start at this address and the address above the last of those written back to the base register when the base register is not part of the register list. Okay, cool. And this is the encoding. I think it shouldn't be, it doesn't have any flags, so I think it shouldn't be too LD. I think we have something similar. That does maybe push or pop did something similar. We have LDR. Okay, we'll do it in a moment. I'm wondering what is this MSR. Yeah. Move to spatial register from ARM registers, the general purpose to spatial purpose register. And there is this, and then sysm. MSR is a system, APSR. So what's sysm? So okay, so I think it could update the flex, the APSR register. It could update the stack pointer. So there are 2 main in process, or primask, which is probably something related to interrupts. Let's take a look at where this instruction comes from. So this is vector entry. Where is this vector entry defined? CRT0 sounds promising. Okay. Not sure what this does. It loads something from this M0 plus CPU ID offset, and then it stores the value in R0. No idea what they do here. But let's see what this is. Reads the CPU, the ID number, the revision, and CPU ID offset. Okay. Oh, MSR MSP. What's MSP? Main stack. So MSR MSP probably activates the main stack pointer or writes to the main stack pointer. And then it ranges, so it loads R1 and R2. And what's R0? R0 is, so let's see, loading R1 from this address. What's in this address? So we are loading this value into R1. What's this? Yeah, that's CPU ID register. So we probably need to read about the CPU ID. Okay. where were we? Vector entry. So we are loading this address of the CPU ID. Then we are looking at byte 8 of the CPU ID register, and then reading two D words into R1 and R2, and probably loading the value from R1 into the MSP, and then calling jumping to the value inside R2. And what's the value inside R2 and R1? We need to read about this CPU ID. It's probably in the datasheet. Register. What's the address of that? No, that's not the one we are interested. That's CPU ID base. Implementer. Huh? That's 8 bits. What's in this address plus 8? Internal registers, perfect, but what are those internal registers? Maybe it's described here. System control and ID register. System control block, okay. CPU ID base register, what's there? So we have implementer, variant, okay, and then okay, I have no idea. ED. Oh, okay, so that's the vector table offset register. It's in this address, and then application, interrupt, and reset control register. Okay, that's the table of the vectors. Interesting. So we are reading it, and then maybe it was set somehow by the second stage of the boot or something like that. Okay. So CRT. It's called vector entry, so it does have M0 plus CPU ID offset, and then adding 8, and then loading and what happens next? Yeah, this is a moment where if I had a real Pi Pico, I would probably just pick it up, connect it to the debugger, and step through this to understand what the real hardware is doing here. But we don't. So first of all, if any of you has a physical chip and is willing to try, that would be helpful. Interesting. So let's see if this code should have been executed at all, like if this is something that always executes, or yeah. So we are doing something that determines whether we should go here, or in any case, like we would go here. Just R0 would probably, so we are reading from reset start. That's probably LDRR0 vectors. Pico no flash. Okay. LDRR0. Let's put them side by side. Okay. So LDRR0, I guess this is loading this into R0, but where is this branch? Oh, okay. So this is doing that, and this is always branching here to vector. So yeah, so this is always executed, and then vector entry is reading from this address into the value here, this value into R1, and then storing R1 R0 into this offset. So what's in R0? Not sure what's going on here. Okay. Let's try to write down what we know. So R1 is getting this value. So R1, I think we have seen that the value that R1 is getting, this value, right? That's R0 is reading from here. R1 is reading from 106. So at 106, yep. So we are reading from here this value. So we know that R1 is getting this value. And then the next thing we are doing in 108, we are storing R0, saving the value of R0 into what R0 is. Oh, okay, got it. So R0 is just, I don't know why we have this. Interesting. Anyway, R0 is just getting this value, which is vectors. Okay. And vectors is defined here. Oh, interesting. So I think I'm starting to understand what's going on here. So, but wait, that's the Bootrom. Is there another vectors here? Yep, there is another vectors here, which has a bunch of vectors. So, okay, so we are loading the address of this table into R0. And then we are just doing what the CPU does at boot. So we are setting the stack pointer to the first value, which is stack top. That's so LDMIA loads these two values into R1 and R2, and then we are setting the master stack pointer. The MSP, that's the master or main stack pointer. We are setting the main stack pointer to the value in R1, and then we are jumping to the reset handler, which is just next to the vector entry anyway. So ideally, we could just set a stack pointer to whatever is there. Where is these vectors? Vectors, where are you? That's here. Yeah. So no, something doesn't make sense. This one. Yeah, okay. So that's the address where the vectors are. And what's at this address? We don't have it. Here we go. This is, oh, without a 0x. So yeah, so basically this is like what the initial value for the stack pointer would be, and then this is probably just reset handler, the address of reset handler 113. Where is 113? Yeah, with the bit. So yeah, so basically this code doesn't do a lot of interesting stuff, but we need to execute it anyway. And then after this would execute, we would just continue running from here. But at least now we understand this. Anyway, let's start implement those two instructions. About MSR, I'm still not sure. We'll probably make it update the stack pointer for now, and then figure out if we need to do something with these two different MSP and PSP, if we need to swap it with them or something like that. We can do it later. Anyways, let's do LDMIA. Where is LDMIA? LDMIA is here. So this is the opcode. Let's create an encoder. How does the register list work? Just a bit mask, right? And it's probably R0 through R7. Okay, that should be a piece of cake. So let's do the encoder for it first. Assembler. Do we have something with LDMIA? It has the RN and register list. Right, RN and registers, that's how they called registers. And then the encoding is just this, then RN, okay, 0B, RN, and it's shifted by 8, right? And just like 3 bits. And then we have just registers, just for the good measures. Make sure it only takes 1 byte, and this is a number. And let's create a test case for it. So assembler spec LDMIA. And this, not LDR, and that was LDMIA blah blah blah, should be encoded. So R0, and this is 0B 0000. I think that's the correct, right? 0 1 2 3 4 5 6 7. Yeah. So R1, R2, or maybe would be a bit more readable. And this should be opcode LDMIA. And we should define a constant for R2 as well. And this should be equal this magic value, and it doesn't equal. Why doesn't it equal? C806. What do we get here? Oh yeah, we need to shift this this one as well. Okay, now it's working perfect. Now we can create a test case for LDMIA. Okay. LDMIA. How did they write it down? R0 to R1 and R2. And that would be opcode. We have this. Okay. So R0, R1 and R2. And then we need to initialize the register. So dot register. So let's say R0 is just the beginning of the RAM, and then it should do the following. So first of all, R0 should be incremented by 4 to point after by 8, and then let's put something inside the RAM. I think we have this SRAM view set uint32 byte 0 would be food, and the next one would be just don't have any idea here, so let's just do it 42. Oh, and offset 4, and then we expect R4 to be incremented by 8 for 2 registers. Too many zeros here, so probably too many zeros here as well. Yep, and R1 should get the first one, and then R2 should get the next one, 42, and we have this assertion for PC, and the test case is done. Let's just double check that register is 0, blah 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 blah. Back. If bit count registers is less than 1, then unpredictable. What does it mean? No idea. Anyway, so for I from 0 to 7, if registers I equals 1, then read address plus 4 if write back and registers n, which write back is just the same condition, then rn plus, okay, yeah, that seems pretty straightforward. Let's implement it then. LDMIA. So if the opcode is this 0b whatever, then we want rn and register list. So rn is just opcode 8 and const register, registers opcode and ff, and then we can probably just implement this with the for loop. Let I equals 0, I is less than 8, I plus plus, if let address is just these registers in rn, if registers and if this bit is set in registers, then we need to address plus equal 4 these dot registers indexed by I is just these dot read uint34 from address. Okay, and then just write back. So if registers, so if that bit of Rn is not set, we only write it back in that case, then this.registers Rn equals address. And I think that's it. It doesn't pass though, because address, what's the value of address? Let's start. What's the value of Rn? It should be 0. It is. What's the value of address? It should be something. Oh, yeah. We asserted on the wrong register. It should be R0. So this one is good. Now the next problem is that we got an incorrect value in R1. Let's print here. Let's focus on this test for now, and let's print the value of I and address. So 1, but 16. The value of the address seems to be good. Let's also print what's at this address. Too many prints and we don't see the results. Okay. Something is strange here. Oh, yeah. As usual, we forgot the true here, because this is Little Indian. Okay, all is good now. Great. Oh, so yeah. So we can remove those logs. Okay, perfect. And one more test. Let's see. Let's just make sure that it doesn't update the register if the register is already on the list. So if we are like reading into R5 and R5 is the base register, then it shouldn't. So R5 and back the address to R5. So if we are reading from R5, and then R5 is the start of the RAM and we have the food, then we expect R5 to have food and not the address. So R5, and let's remove this from filter. Yeah, it passes. Great. So we tested both with write back and without write back. We can see that if we focus on this test, this line is great. It's not executed. So perfect. We got one more instruction. That's perfect. Let's start, and yeah, one less. Yeah, these are to the MSR, and then there is the BX. Okay, anyway, I think it's been like 2.5 hours already. So we have like those instructions, and we spend a lot of time like looking at the how to encode this BL correctly, but we cracked it. And I think we can sort of wrap it up. It would probably take like 10 more minutes to do this, but we can leave this for the next week. And then next week we'll probably go, and I guess, you know what, let's just run it forward a few more instructions, because we know in any case those instructions don't affect the flow. So let's go to run link, run it like 50 instructions and see what happens. Yep, it goes wrong at some point because of those other missing instructions, like what's here. That was 11A. We don't have this add probably. Yeah, it's probably missing this variant of add, and then what's 14E. Yeah, we know we are missing BX, but here this is actually a return. So since we don't execute this instruction here, we got into this data that we start executing, and then we get all sorts of weird behavior. So I guess for next week we will need to finally implement. Do we have this? Oh, we needed it below. Anyway, so for next week, I think we'll finally have BX. We'll implement BX, and then probably this one and the missing add instruction, and then who knows? Maybe we will get past the reset handler and all these stuff. And where does it go? BSS field test, and then BSS field loop. Oh no, platform entry, and then where does it go from here? Platform entry plus BKPT. We need BKPT. No idea what is that. Yeah, I think this one already. What does it do? It loads some address into R1 and then jumps there, and these are the addresses that it loads. What's here? This one. What's this? So it jumps to. Huh? Not sure what's going on here. Yeah, that was platform entry, right? So let's see what platform entry is doing. Yeah, so platform entry is just jumping to runtime init, main, and then exit. So if we get to this point and we can get through, I'm not sure what does runtime init do. And we get past, oh, it doesn't do anything? Oh, yeah, I'm not sure. Let's see here. Yeah, it does do some stuff. It's provided by platform. So if we get through runtime init correctly, which probably calls a bunch of other functions, but once we get through that, we actually jump into main, and I think we have seen that we already know how to execute from this address from main. So maybe next time there is a hope that we will get to the point where we can just load arbitrary program and it will start executing without us needing to tell it where to start to pinpoint the address of main. It will just execute all the code and get to main. I'm optimistic, but that's the way to keep it there, to keep it going. So I think we'll wrap it up for today, and let's copy those two. Meeting is important. Don't need the hex file because we already have it in this type script, but let's add a comment here. rpi or rp bootrom binary compiled from, what's the rp bootrom, yep, built from revision. I think they only have like 2 commits in this repo, so it should be pretty easy, like B0 and B1, so that's what we have. B1, the newest one. Okay, so that's the Bootrom, and then we added a bunch of new instructions: BL, LDMIA, and LSRS. 3 new instructions. And a lot of explorations. Oh, one more thing before we, so this is fine. Before we commit, let's close these windows. Before we commit, oh, I didn't. I just wanted to comment out this and start from main for now. So if anybody runs this code, or did I not do that? Huh? Yeah, why does it start from, where is run blink, which is no longer blink? Okay. Interesting. I expected it to start from this address because this is commented out. Oh, and it does. Oh, I get it. So UART no longer works because now we have BL, and BL is going to all sort of interesting places. Like, I don't know how, but we end up running from this memory address. So that's another thing that we'll need to look at. Probably this missing instruction is derailing us. Let's see what's there. Yeah, probably this forgetting this, not doing this move is eventually hitting us. So yeah, we'll need to implement that as well, part of UART init, and then we can probably get Blink to work again. But right now Blink is broken because we have BL and we didn't have it before. So today we RP 2014 implement BL, and what else? So we had BL, LDMIA, LSRS, now Blink, now hello, UART is broken, but we'll fix it next week. Hopefully. Missing, we need to implement VX. So list of instructions that we already know that we need to implement is like, I think it was here. Did I delete it? But I remember it. This is BX, and what else? That was like train instruction, the beginning, vectors and MSR, and we have spotted some add instruction down the road. Let's just copy the TARS thing because this is useful. So MSR. So next week we won't have to ponder what we need to do. We will already know. And this one was missing, and then we had that move in UART init, that UART init. Where is that? Yep, this one. So yeah, we need to have 4 more instructions, and then who knows, maybe we'll have this program running. And I think after getting to that milestone, we can probably either start looking at either the PIO. I know that many people are interested in some kind of simulator or emulator for the PIO, so we can start looking at that. Or maybe we can get ambitious and try to get MicroPython running inside this simulator. So let's give it up to decide for next week. Anyway, so yeah, also need to implement, we just need to implement at least these ones, and I think that's a good time for commit and push. So let's commit and push. And that's it. So thank you very much for joining me. We have 8 people still on the stream. Pretty impressive. So thank you so much for joining me to this live stream today. And next Tuesday, we will continue where we left off. And as usual, if you have any questions, then we have the Discord. I will put the link in the chat. So walkway.com/discord. Thank you, Ekari. So you can catch me on Discord, and if you feel like just sending a pull request and adding like those missing, I think we have only a few that we don't have the assembler for them, like for BNE. So adding those opcodes to our mini assembly, that would be really cool. So if you feel like working on that and sending a small pull request. That could be really cool for next week. Anyway, so have a good night or rest of the day, and see you next week. Bye bye.